Hello everyone again and welcome to our machine learning tips. So today we'll be looking at another type of assembly method also built from decision trees, which we call it the gradient boosting techniques. These assembly methods are mostly used for reducing bias and improving accuracy in most real-world applications, whether it is a regression or classification problem. For the case of random forest, I earlier mentioned that if we are having a problem and we know that we are trying to reduce variance, especially for maybe stock predictions, something like that, or maybe price forecasting for maybe flight prices, we can use the random forest. But if we know that we are trying to look at a problem that is trying to reduce bias, we can try to use the gradient boosting assembly techniques. So the motivation, why are we looking at these gradient boosting techniques, is because earlier mentioned decision trees, they are simple, but they have like high variance and they can easily be, introduce a lot of bias when training them. Also, I did mention earlier that random forest reduces variance by using the bagging technique, where we first of all do a random sample for the training data and then train multiple decision trees and then end up, if it is a classification problem, we are looking at the majority voting. If it is a regression problem, in the case of random forest, we are looking at the average for all those trees. For the gradient boosting techniques, these methods are used to reduce bias by sequentially improving errors. Sequentially is because gradient boosting techniques are trained by building trees in a sequential method. So what is these gradient boosting techniques? These are actually assembly methods where models are built sequentially. So what happens is that each new learner focuses on correcting the errors of the previous ones, which simply means that, for gradient boosting techniques, they train our decision trees sequentially, which is like we can just say in a linear method where, the error made by the previous tree, the next tree tries to correct that error as much as possible, mostly focusing on the misclassification that the previous tree uh, did not see. Or maybe if it is a classification problem, if the first tree did misclassify some classes, and then the next tree will try to correct that error, and then at the end you will see that the accuracy of that model will be increased as much as possible. And then the final model is like the weighted sum of those weak learners. Often, they are often what? The shallow trees. One thing you have to note here is that with gradient boosting techniques, you can actually define a loss function because it is a sequential method. You can use that loss function to optimize it until you get what? Those weighted sum for those weak learners. So the core idea of gradient boosting is start with what? With a weak model. That weak model is like a decision tree, and then it compute the residuals, which are the errors, and then they feed a new weak learner to those residuals that are computed, and they add learner to what? To the assembler with some learning rate. You repeat that process until what? The performance of that model is is much better as possible. So the role of those gradients is what? The gradient boosting feed weak learners to negative gradients of what? Of the loss function. One thing we have to note here, we already saw these different loss functions for regression problems. It is the mean squared error. If it is a classification problem, we can use the log loss. So the next, when we have feed these weak learners, we allow optimization of what? Different loss functions. For the regression, as I did mention, it could be the squared error. This squared error here is what? The mean squared error that we have seen a lot for regression problems. Also, if it is a classification problems, we saw the log loss for when we did logistic regression. You can go back and watch that video, or also you can use a customized loss function where you can customize that loss function based on whatever function you are trying to allow that model learn. So one thing we have to note here is that the difference between the gradient boosting algorithm and the random forest is that random forest is a bagging approach where we train trees in parallel. Parallel in the sense that the first thing is that we first of all have to do some random sampling for the data, training data, and then we train these models with that random subset. Um, and then we end up, if it is a regression problem, we look at the average. If it is a classification problem, we look at the majority vote. And then for random forest, it ends up reducing what we call variance. Remember, for the first start of the these machine learning tips, I did mention that most machine learning models, what we are trying to do is to reduce variance and bias. With the gradient boosting techniques, we train trees sequentially, which is like an additive method, which ends up doing what? Reducing what we call bias. So the important hyperparameters, as we'll see in most of the labs, for these the gradient boosting methods, we already saw this X method, which is the number of boosting rounds. Here is just the number of trees, and then we also we also look at the learning rate, which is like the contribution of each tree in that sequential method. And then we also look at the maximum depth as the maximum leaf nodes, which is like the complexity of those trees, and then the subsampling, which is a fraction of data used per iteration. So the advantages is here that with since we are building weak learners, they are very, very good if we are looking at models that are very high in predictive accuracy. Also, they are flexible in the sense that they support different loss functions. That is the key advantage of the gradient boosting algorithms over random forest. Also, they work very well with structured and tabular data. So the limitations of this approach, because we are training trees that are in a sequential additive method, they are slow to train compared to those bagging methods. Bagging methods are the parallel approaches, so they are pretty fast in training. They are very sensitive to the hyperparameters that I did mention in the previous slide. So we will be doing this when we go to most of these labs. We are going to be looking at different ways we can optimize these parameters using grid search. We can use the Bayesian approaches, as we are going to see as we move on into this lesson. They have that high risk of overfitting if there are too many trees, or the depth of those trees is pretty very large. So the applications, they are used a lot in credit scoring and fraud detection. They can be used in click-through rate predictions, that is especially these ads that we see. You know, maybe you're watching a video, you see some ads. Most of those ads that we see are actually built using machine learning. Also, we can also use it in medical risk prediction. They are also popular in cargo competitions. The gradient boosting algorithms, they are very, very applicable in most real-world applications, especially in credit scoring, maybe trying to predict if someone is going to default or not, if they give them a credit card, and so on. So the modern implementations of these methods, first one is the extreme gradient boosting algorithm, which we call it the XGBoost, which is optimized. We can also use regularized method that can prevent overfitting. We already saw the different types of regularization techniques. Another type of the gradient boosting algorithm is what we call the light gradient boosting machine, which is efficient with very large data set and leaf-wise growth. We also have what we call the cat boost. This one can handle both categorical variables directly, where you don't really need to bother about the one-hot encoding and so on. So the summary for this lesson is that we looked at the gradient boosting methods, assembly methods, which they train trees sequentially, that is in an additive method. These approaches are very good at reducing bias by forcing on difficult examples. They are very powerful, but need careful tuning, especially just to prevent what we call overfitting. The foundation of the gradient boosting algorithms we are going to see in the lab is the extreme gradient boosting method. We have the light gradient boosting machine and the cat boost